Well, hi, good morning. Thanks so much for joining me here in my shop. I'm doing something a little bit different with this video you're about to watch. I was in my shop yesterday working with my precise tube tester here on the bench, and really that's the video that's coming next, where I take this tube tester and try to exercise its three very interesting functions that most tube testers don't have, and that's reading the plate current and a couple other things. So anyway, I'm going to let that video play after I finish talking here for a couple of minutes, because in the middle of that video you're going to see me get one whopping shock. Something I really don't want to have happen, of course. In a shop like this there are, of course, shock hazards of a number of sorts. One of them in particular is the one that got me yesterday. I didn't suffer any kind of injury, and I don't think it was a shock substantial enough to have actually really injured me. But it kind of motivated me to make some changes in my shop here to try to reduce the possibility of a similar shock. So that's what I want to show you a little bit of, and then you can watch the video and you can hear what I say when I get electrocuted. That's a bit of a strong word, electrocuted. So what's going on here in my shop, and this would be true in any vintage shop or shop with vintage equipment in it. Newer equipment comes with 3-prong plugs on them. I'm pretty sure all the new testing equipment, if you were to buy it and put it in a shop like this, comes with a 3-prong plug. That third prong, the ground prong, is connected directly to all these cabinets if there's a 3-prong plug. Consequently, all the metal cabinets are connected together at the end of the 3-prong plug, and there can never be any voltage between them. And there can never be any voltage on the cases with respect to the ground wire, because they're hooked right up to the ground wire. That's great with 3-prong equipment. There isn't a lot here to worry about, although you got to be well aware that your shop is grounded. But in a vintage shop you usually end up with a mixture of equipment. Older, newer, and in varying states of disrepair, I guess would be the best way to put it. So if I just point with my finger, I'll just show you. Okay? That's a 3-prong. That's a 2-prong. That's a 3-prong. That's a 2-prong. That's a 3-prong. That's 2, that's 2, that's 2, and another 2 over here. Most of the radios I work on are 2-prong plugs. The radios come in 2 versions, dangerous and really dangerous when it comes to this kind of stuff. I'm not going to go into that. I just want to talk about the shop. So with a mixture of equipment like that, there's very likely a 60 volt, 50 volt, 70 volt pressure, AC pressure, on the cabinets of a lot of these 2-prong pieces of equipment. Now that voltage, even though you could read it, like I'm reading it right here, right now on my meter, 62 volts. Okay. You can't draw a lot of current because that voltage is coming through something to restrict the current. Either a capacitor, a resistor, or a combination of capacitor and fairly large resistor, like a couple hundred thousand ohms. So if you do manage to touch the cabinet with 60 volts on it and then touch the grounded thing, which I'm not going to do, the 60 volts shock you get, well, first of all, the 60 volts will probably drop way down, and with any luck you won't even feel it, because humans are fairly insensitive to electricity. Not like cows. Cows can feel 3 and 4 volts between their hooves. But we can't feel 3 or 4 volts. We really can't feel things till, I don't know, never really checked this out, 40, 50 volts, somewhere around there, I don't really know. 60 you can feel, I know that. So what to do here? Getting a 60 volt shock on a properly working piece of equipment in a situation like this is not particularly dangerous, other than it's going to make you jump and jerk. And it's not pleasant. It's getting the full 120 volts that is dangerous. So what I've been doing, as you know if you've been watching my channel, I've gone through all my equipment, I've checked it all out, I've looked for all those situations where the case could be live with a oomph behind it and tried to correct them. I then made a choice to continue with my shop with two forms of grounding in it. One is kind of solidly grounded through the third prong, and I just be aware that this piece of equipment and this piece of equipment and this are grounded that way. So when I draw leads out of them, sometimes that lead, the ground on it, is actually guided right back through this piece of equipment, right back to the hydro ground. And I've tried to maintain an awareness of this, which I think you have to in a shop like this. You have to know what you're doing. I should have said this right at the start. The primary way to be safe is to know what's going on in your particular shop. So, not that my previous arrangement with what was particularly dangerous. The way I got the shock, I'm going to explain next after I finish this. But I'm tired of getting the little brush shocks here and there from this kind of equipment. So I've decided to ground the cases. This is just a different way of doing it. Ground all the cases back to the power line ground. And I'm going to do it by using a terminal on this beast over here. This is basically a ground terminal tied to the cabinet, tied to the third prong. And I'm just going to run this green wire, which you can see. And I'm going to have little lit tap-offs come up and pick off the ground point, or in many cases, a cabinet screw, because they actually don't really have a facility. So I just pick a screw on the cabinet, screw a wire under it, bring the wire out. You can see it here, it's waiting. One of the things I want to do just before I connect those wires permanently or semi-permanently is measure the voltage that exists, and then arrange the power plug to provide the least amount of voltage. Now if you look at this guy, let's wake him back up. So it says 62 volts. Now if I take the plug, and this is plugged in behind my bench, I pull it out and reverse it and put it back in, this is still going to say about the same amount. It's not going to make any difference, and this is good. This is what you want. If I have a piece of equipment in here and I hook it up this way, this is just a voltmeter from the case to the ground, and I read 95 volts, well then I might start thinking something's a little out of sorts, and I would be inclined to pull the plug out, rotate it, put it back in, and see that this voltage drops from 80 or 90 down to 30 or 20. And then I would hook up the ground wire and leave everything plugged in that way. One way or the other, it doesn't matter all that much. It's just a preference I have. So I've also thought a lot about, I've been thinking about this for a long time. I just got motivated to go ahead and do it. I've decided to use a fairly floppy kind of wire. I'm just going to kind of tuck it under the equipment here. I had thought about bolting a nice bus all along here and doing a real fancy job. And in the end I concluded that's too much work, and it leaves the shop with too much inflexibility. Occasionally you have to pull this equipment out, you got to pull stuff out, do stuff. So I wanted to maintain flexibility. So it's going to be a loose wire, and if I do need to pull a piece out and disconnect it, I mean, I can obviously just take the wire off the screw in the back. And again, as long as I know what I'm doing, and you might say, well, you must not know what you're doing because you did get a shock, which I'm going to talk about in a second. I should be able to maintain my safety a little better in here once I have this done. Okay, now how did I actually get a shock? So I have a piece of test equipment, a new tube tester that I've been reconditioning. I'm at the point where I've reconditioned it enough that it's functioning, and now I want to find out how well it's functioning. So to do that with a tube tester, you have to compare it to other tube testers. I don't know how else you can really come to grips with its function. And so I've been doing that. I have a number of tube testers. I've been doing all kinds of tube testing like crazy. I had this big tube tester, the precise tube tester on my bench, the one that I've been working on. I had not gone through the process of checking its case grounding yet or anything like that. I really hadn't focused on that. It's a two-prong piece of equipment. I could have plugged it in here. This would be great. This power supply is fed from a transformer, and there is no circuit path between the power coming out of here and the hydro ground. But literally, and I would never do this, but literally you can shove a screwdriver in here into one prong, grab something grounded, nothing would happen, pull it out, stick it in the other prong, grab the thing, nothing would happen. Not going to test that, but that's the theory. So anything plugged in here, you should not be able to get a shock off it. That truth disappears the moment I apply a ground via this test equipment to the item that I'm testing. Therein lies the benefit of the two-prong system. Two-prong system, often the ground, this ground wire, is not in any way grounded back to the power system. That allows more flexibility in testing, which I won't go into. There are issues with hooking up ground wires, more than one. If you hook up more than one ground wire on a radio, you better know what you're up to before you do it. So that's going to introduce a little more concern with using this test equipment over the way it is now, once I ground these cases. Some of the equipment, the case ground is not connected to the actual test ground. These ones are. I managed to make that observation. So I know if I ground the case, this black wire has the same grounding onto the green wire and out that ground terminal over there. Wow. So, you know, I don't like doing instructional videos, although it may sound like that's what I'm doing in here. I'm really not. I'm just doing my thing in here as best I can, and trying to, you know, progress and learn and do better and fix a lot of radios. I really want to get a lot of radios fixed, and you're welcome to watch and learn from the things I'm doing. Watch out, you can learn some wrong stuff from me too. I'm not suggesting I've got it all sorted out. Obviously I don't, or I would never have gotten that shock yesterday. So how would I prevent getting a shock? So I'm going to reinstitute something I was doing in my old shop before I set this one up, where I bring out a wire that runs through an ordinary light bulb. It was a Christmas bulb, a little red Christmas bulb. Bring out the wire, connect it to the chassis of the item I'm working on, even if it's plugged in here, and then have that. This is creating a problem. I'll finish my statement anyway. Then have that wire, the other side of the light bulb, connected to proper ground. And what will happen then is, if the chassis comes alive relative to the earth ground, the light will come on. This is pretty handy if you're working on all-American 5 type radios, 5 tube radios without a transformer. And if you don't have any way to isolate them, oh my God, you're really in a scary situation there. I have an isolation transformer. Without the isolation transformer, you had better grab your voltmeter and pay a lot of attention to everything. Now, I'm not going to go into that issue. This isn't the right time to do it. I've already talked too much. Almost 15 minutes of listening to me yap here. So, last thing, a little more yapping. So I'm making this measurement to get the plug plugged in such a way to get the lowest reading on here, or 60 is fine too, before I make the final connection. Once I make the connection, all these voltages are going to disappear, and I won't ever know again which, if I plugged it in the right way or the wrong way, which is probably inconsequential. Anyway, I'm just being overly fastidious with all this stuff. Okay, so I finished fixing up my shop here. You can see my ground green wire. There isn't a single piece of equipment whose cabinet is not connected back to the hydro ground here in my shop now, either via the third prong on the plug or via this green wire and the small yellow wires you see that are attaching to the equipment that only has 2-prong plugs. So this doesn't make my shop super safe. Again, I have to understand what's going on in it to be safe, same as anybody in any shop environment or anything like this. And I just want to draw attention to the fact that what I've done here in no way would prevent the kind of shock I got yesterday, or that you're going to see shortly actually. That potential is still there. So to control that potential shock hazard, and that is having a piece of equipment on my bench where the box, the cabinet, metal cabinet is live, or other parts that you can just casually touch are actually live at 120 volts. I made this arrangement. So I have here a ground wire that I'm going to commit. It's always going to be hanging here. It'll always be here unless I'm using it. I can simply plug it into the ground terminal down here, which you can barely see. What I would do then is take a voltmeter, even before hooking up this wire, and I would look from the case to ground and see if there's anything there. If the unit's off when I do that, I would then switch it on and test again. It's really critical that you test it both on and off for reasons I won't go into just now. And if I'm still nervous about it, I can clip this guy right onto the cabinet, and now the cabinet and the item I'm working on will be held down at ground potential. When I'm working on things, I normally plug them into this isolated outlet here, but once you hook up any piece of test equipment, a ground has been applied to the unit, to the thing I'm testing, and this isolation transformer is not providing any kind of isolation at that point. So just things I have to keep in mind. And how did I really get myself into this state? So I brought a piece of equipment into my shop, started working on it, decided I would put it to work, and up until that moment, that piece of equipment, the precise tube tester, had been plugged into here, plugged into an isolation joint. And that's probably isolation transformer. That's probably why I didn't get any shocks off it or notice any problem, and I wouldn't even be concerned, frankly, terribly. But when I went to use it, as you'll see in this video, well, you won't see it, but it's plugged into a regular outlet for the first time, more or less. Okay, enough talk. Let the video roll. Well, hi, and thanks for joining me here in my shop. Today I'm going to be working with this precise tube tester, something I'm trying to get comfortable with, and I've just discovered that it has some features in it I wasn't expecting. Ways to measure things like plate current and the like. Things I'm quite interested in doing at this point. So I've decided I'm going to teach myself the 3 unusual tests this thing will do. That's measure any element current, like plate current, screen current, that kind of thing. And also this will measure a couple other things which I don't know if any other tube testers really do it. So we're going to check it out. Now we're also going to look at the kind of signals that are being put on the tube here. That's why I've got meters laying out here and that. This meter in particular is set up to measure the element current. Right now this tube is set up so the plate is the element I'm testing, and the current flow into the plate will show up here. And my first test of this, wow, it seemed to really work. And I got a little more curious and decided I would look at the kind of signals that are being put on this tube tester. You can see my scope in the background here, and that explains the scope leads that are sitting here. This is a tube extender, and these are terminals that allow me to attach to the various terminals of the tube very easily. That's what's going on. Normally you couldn't do this kind of thing. And you see these 2 connections here. Oh, you can't quite see it, but there it is anyway. That's plugged into the plate and the grid terminals. But these terminals are being used in a special way because of the setting of these 2 switches here. And can't forget it, there's another one that needs to be set. This one set to so this is to cause the plate current to want to flow between these 2 terminals. So if you hook a wire between these 2 terminals, the plate current flows, and I very cleverly put a meter there. So that'll read the plate current. Let's try it out. So just raise this my camera up a little bit here. Get a little better idea of what's up. That's better. That's a little better. Okay, let's just move this out of the way. There. And I'm going to move this one out of the way so it's a little clearer. And you can see the current here. It's going to be in milliamps. First, we'll check the line. Now you probably haven't, well, you can't really see this meter, but that's okay right now. And the bias is, here we go, beeping meters. So that's this meter beeping here. Let me just keep it happy. There. That'll keep it happy for 5 or 10 minutes. The bias is supposed to be 3.6 on this meter. I'm just checking it now. Yeah, it's 3.6. Everything is good. Okay, so we'll put this on test. So now I'm going to move this for a moment. I'm going to watch the meter on the tube tester here do its thing. So this is going to show the GM for half of this tube. This is a two-part tube here. Here we go. Okay, just ignore this meter for now. Ignore the scope for now. You're not supposed to see those things just yet. So what do we see? So here the GM has come up. I have to check this. I'm on the 8K scale. 8K scale. So this is just under 2,000 mhos. And that's the grid-to-plate transconductance. Is what it really is, if all said right. Now, let's look at the plate current under this circumstance, which you probably already looked at. Okay, 8.7 milliamps. 8.7 milliamps. If we look in the manual here for a 6SN7, we see, in terms of plate current, you may not be able to see that on camera, but that's okay. Plate current under two circumstances is 10 milliamps and 9 milliamps. So 10 milliamps under all these settings, and of course we have no idea what this guy's doing, what the tube tester's doing. That's what I'm trying to find out. And under a plate voltage of 250 volts, you can get a plate current of 9 milliamps. But of course, you have to have other things set correctly, like for instance the grid voltage. So I don't think there's 250 volts on this tube in this tube tester right now. I think it's more like 150. Why do I think that? Because I have this meter reading the actual plate voltage. So if I turn it to test mode, you see it go a little over full scale. That's the 150 volt scale. I'll put it on the 500 here. Okay, and so we're reading about 170 volts, somewhere in that range. So that's what it's got. That's what it's putting on the plate of this tube. So 150 volts, and there's no way we can look at this and look at this or anything really and sort out what should be the current and what should be the GM. It's not quite true what I just said, but as usual, I'm talking to myself a little bit here too. You know, this is all kind of new to me what I'm doing. Let's hit the test button and read the actual current here. 8.6. Now, if I just wiggle the bias control a little bit, here it is here, this, just a little bit, and you watch the current. So it'd be pretty easy to have this control set wrong and drive the tube current up quite high. So 20 milliamps is about the highest you want to go. Now let me put this on bias, and we'll reset the bias again to where it should be according to the book. Not the tube book, not the tube manual. No. According to the chart for this tube tester. Okay. So the question I have now, everything's set right, everything's working fine. Is there really 8.6 milliamps flowing through this tube? And this is an RMS meter, but you've already seen what's on the scope, and you know it's not at all a straightforward AC signal. So right now we are looking at the grid signal. So this will reflect, let me move it up the screen a little bit. This is going to reflect the signal being applied to the grid. Scope settings are 5 volts per division with the lead set to times 10. So it's actually 50 volts per division. So this is what they're putting on the grid during the test. Okay, let me flip this to DC here. We're not. Watch now. Here we go. There we go. So you can see that there's a negative bias and then an AC signal, but this is not a smooth AC signal. This is a bit of a chopper there. Let's put it up. It's really quite ugly, in fact, what it looks like. Okay. Now I'm going to change the scope. We'll look at the plate. Let me just put the plate line on. 5 volts times 10, 50 volts per division. Test. $50, 100, 150. So around the middle is 150. Wait a minute. Yeah, that was close to the 0. Let me move. Okay, everything's fine. I just got a heck of a shock there. Okay, well, I gotta stop what I'm doing and investigate how I managed to give myself one heck of a whop just now. Sure felt like 120 volts. Son of a gun. Boy, I really don't know what I was touching. Okay, I had to stop and just calm myself down and think a little bit. I get very upset when I get shocks like this. I get really upset, so I'm going to just stop for a little bit and think about what's happened here. Okay, I think I'm ready to explore what happened to me here. I did look back on the video. You probably have also. And you can see my left hand is busy up here. You can't see my other hand. My other hand was down here somewhere. I think I had it on just on the chassis here like this. I can't really remember. It looks to me when I look at the video, all I'm doing is touching the scope lead right here. I'm all so nervous now. And shame on me, I'm very embarrassed here. I usually check for these kinds of voltages before I get going on stuff, and I know, I know I've got the ground of this device not necessarily not on the chassis here, but actually somewhere in the middle of the circuit here. It's on the cathode of this tube. Now exactly where that is in relation to this whole tester, I don't know. By the way, I haven't turned anything off or anything. Everything is just exactly the way it was. So I have brought in a meter here so we can poke around. I usually do, I'm just so embarrassed. I usually do some pretty simple tests on things like this. This is a two-prong plug device. Those things often have a measurable voltage on their cases and cabinets. The voltage is getting there usually through some high resistance or a small capacitor. So if you do draw current from it, the current is limited, strongly limited. And I think that's what actually happened here. I think I drew current through some kind of current limiting thing, even though, boy, it did not feel that way to me. And let me tell you too, my attitude about this, I get the odd tingle shock now and then. In a shop like this, it's hard not to get them. Or sometimes they're called brush shocks. You just touch something, you get a small buzz, and that's from 50-60 volts with a lot of current limitation, as I was just explaining. When you get a full shock, of course, your muscles hum, everything hum. I mean, you can tell the difference between a current supplying shock and a little tickle thing. This was a heavy shock I got. I got it right between my hands. It's the worst thing in the world you can get, right? Is a shock between your hands, because you're going to have electric stress right through your chest. And guess what's in your chest? Yeah. So all bad in every direction. Here we go. I have one lead of the voltmeter hooked up to this screw here. So it's the case voltage, which I believe I was touching. I'm just gonna, my hand was in here, I don't really know what it was. Let's just take a look on this meter here. This is set to AC volts. There's nothing there. Notice that I've turned it off at test here while I'm doing this, by the way. Nothing. There's nothing really happening here. Okay, let's put it back on test. Oop, test. Lock it on. Oh! I said oh because I saw 110 there for a second. Let's try that again. Try a few other things here. So this is my SDR radio, and it's really connected to the computer. 60 volts. And what about up here? 88 volt. let me clip this on something here. So 60 volts is indicative of the situation where you have the two-prong plug and you have a capacitor or a large resistor tying one side of the line onto the chassis. You get this kind of voltage reading on a high impedance meter. If I took a low impedance meter, I'd probably see nothing there. So let's take it off test. Oh my gosh. Oh. You wouldn't expect anything to happen to this just because I put this on test. Wow. I'm really not feeling good at all now. What is getting on the cabinet of this thing? Let me read the voltage. So I'm on the cabinet here. I'm going to connect it to the, I don't know what. Well, what else is there I can hook it up to? Hook it up to the cathode of this tube that's under test. Right, so I had this DC meter connected. I'm now connecting an AC meter in the same place, but we know there's an AC signal there. Nothing now. There's the DC. Nothing. Okay, let's try from the cabinet here to what do I do with my meter lead? You know what? That was not on the cathode. Oh. Oh, interesting. So the cathode is basically connected to the chassis here. What about voltage on the cathode? Well, that's what I'm doing when I do this. I'm actually reading cathode to the cabinet. Perhaps I have this equipment hooked up. I'm transferring a voltage out of here and onto some of my equipment, which has then shocked me back. I don't know. Just another thing I've realized too, when I have this tube extender here, I have these terminals sticking out everywhere, and man, you can easily touch those terminals. Particularly if you try to withdraw the tube extender while the set's operating. What to do. I don't feel any certainty about not getting another shock. That's why I can't stop here. Well, let's try something simple. Let me put this back on the red one here. Jim, come on. Too many leads. Here it is. I'll put this back on here. What was I even thinking? Oh yeah, I'm going to reverse the plug on this. So I can put this on hold. You see the voltage? If I reverse the plug, I'll bet you it just comes back at 60. So I'm pulling it out and sticking it back in. Probably get the same voltage there, 60. It's the other 60 of the 120. So that didn't eliminate anything. So I'm sitting here with 60 volts between the case on this and this. I said, why not just run a ground line from the scope onto the chassis? That'll eliminate it, because I already have the scope grounds connected onto the tube here. Let's take those connections off and see what kind of shocking tests we can take then. Okay, so the scope, I'm going to remove the scope entirely here. This could boil down to a capacitor that I should have detected and changed earlier when I was doing some work on this tube tester. I just haven't gotten to investigate these things yet. Look, it's cost me. Oh, it's really upsetting. I'm really upset. Now we check for voltage again. Oh my gosh, the situation's going downhill. Yikes! Yikes! Huh. Now I'll bet you if I reverse the plug, that will mostly disappear. Now, do I have any other equipment with ground? You know what? I do. I have the whoops, not this. This is fine. I have this guy hooked up. Not anymore. I have the voltmeter. Okay, never mind. Okay, so this meter is really not going anywhere. Okay, it's just coming out and going in, so to speak. So changing that's not going to change any of these shocking effects. 100 volts. Wow, that's probably what I felt. Now let me reverse the plug down here and see if we get 20. Isn't that reassuring? So this is a little too much for me to explain really clearly. It's not really clear in my head either. Wow, let's put it on test and see what happens. Nothing. But I'm willing to bet if I connect the scope grounds back to the cathode on this tube. So what is the cathode voltage on that tube as compared to let's say the cabinet here? So I can do that. Cathode. There's two cathodes in this tube, so there's lots of ways to get this wrong. 6SN7. So we're on, it should be number 6. Pin number 6 is the cathode we want to get on. Pin number 6. So this meter is now reading the voltage between the cathode of the tube under test and the cabin. Nothing there now. On AC. This is an AC test. Nothing shows up. Not terribly surprising, just to be sure. We'll put that on DC. That's really not very surprising. So So where are you with forgetting the shock for the moment, getting back to what I'm actually trying to do here. So what I found was 8 milliamps flowing through the tube when the tube is operating, based on how this guy operates it. You can see it doesn't put DC voltages on, it's got some weird stuff that we saw on the scope. Seems to work fine to me. I don't really quite get how such strange signals in a tube can result in a fairly accurate looking current reading, but perhaps this thing will take any type of signal and RMS it, so to speak. So that's interesting, though. That shows us the plate current. It's really a very interesting machine. This tube, you could look at plate current, you could look at cathode current, same thing basically in this tube. You can even look at grid current. Well, I don't think I got a meter sensitive enough to follow the grid current in microamps, and I think this is a really important factor. Okay, wandering all over the place here, kind of as usual. So I succeeded in, let's go back to really what I'm trying to do. I'm trying to do 3 specialized tests on this machine without getting electrocuted. So I've done the first test. The first test is the ability to read current through one of the elements in the tube. I've done it with the 6N7. Got 7-8 milliamps. Looks perfectly normal. Varies with the bias. Excellent. So now what we're going to try is the next test, which is to set up different kind of biasing. Grid leak biasing. So let's set that up, and I'm not even sure why you would want to, but it's in the manual. Let's do it. Okay, I think I'm ready to try this grid bias technique, grid leak bias technique on here. So rather than the unit control the bias through the bias control, the bias is going to be set by this little circuit here. It's a little hard to see in the camera, I just noticed. So all the stuff behind the board doesn't mean anything, behind this board doesn't mean anything, it's just parts I'm saving. This is the little circuit here, there's nothing to this, it's a resistor with a large capacitor across it. A 250 volt resistor and a big 50 volt capacitor. I think this is 1,000 microfarads. In the instructions it says you need at least 500 microfarads of bypass on this test. The bias control is to be rotated to 0, and then you're supposed to complete the test in the normal way. What happens if we flip this to bias? Whoa, I see a huge bias over here. Is that from this? No, it's from this. Okay, so I don't understand fully what's going on. I'm following the instructions. Set that to 0. Test. Should read the same GM as before. Oh boy, here we go. Well, I don't think it's anywhere near it. C8. So that's about 650. Okay, let's just carry on. I'm just practicing along here, but the next step is the interesting one. If the next thing I do works properly, we're going to see the characteristic curve of that tube on my scope. Oh my god, my scope again. I'm going to get a shock. Okay, let me see if I can get this going. Okay, I've hooked up everything just as it explains in the manual, so I'll explain it to you. The most curious thing is this down here. This is just a transformer I've grabbed. It's producing 20 or 30 volts AC, and that's used on the scope as the sweep. And that's why this is sweeping right now. So this isn't a normal scope sweep where it goes across and blanks on the way back. This is going to be doing this. If I could take this flat thing and turn it, you'd see a circle here. So it's going back and forth. As long as that sweep matches what's going on in here, then we should see something useful. That's the whole idea. And I think all I got to do is flip this on to test. I think that's all it takes at this point. So I've made certain changes in the settings of these switches, again in accordance with the wait a minute now, have I? Yes, this one's on 8, so this is the cathode onto switch number 8. That energizes this switch, which is the switch for, I hope I got this right, for the plate jack. So it drives the cathode circuit through the plate jack out through this one resistor. Now the capacitor and this resistor are not involved, just a resistor, no bypass. Oh, there's a little bit of heat in there. How do you like that? So this is a smaller resistor, the 75 ohm resistor as suggested, and the scope ground terminals are connected to the ground terminal here, which I know from previously looking at it. This is connected to the cabinet. So the scope grounding here is not like it was, where it was up here on the tube. So hopefully there's not a shock hazard here. Hold on, stuff popping off. Yeah, this may not stay on here. Okay. So if I hit test, what I'm expecting to see is some kind of curve here, but I really don't know what. Let's see. What do we get? How about absolutely nothing? How about that, Jim? So what's going on there? So we're on DC. Both these are set on DC. This line's coming around here. It's across the resistor. Resistor is connected to the plate. The other side is connected to the ground. I feel like they're making contact. Let's try again. Apparently I haven't got something set right here. Maybe I got this just ridiculously insensitive. Let's crank up the sensitivity here. Try it again. Oh, there we are. Now we're seeing something. Now what is that supposed to mean? I've made, it looks like a toboggan, basically, a toboggan on my scope. Well, a classic set of tube curves, of course. There's many of them in the book here. I mean, you just see them everywhere, right? And I didn't develop these on my own, using my own test jig. So I'm kind of looking for something like that, but it's not going to be a family of curves. It's going to be one curve, like that. And apparently, you fool with the bias. This bias isn't set at all right. The bias is not set right. Off. Bias. The bias was crazy high. Let's bring it down to where it's supposed to be 3.6. It's crazy high. Because of the previous test, I had to set this to 0. 0 on here actually drives a very high voltage on the grid. Here we go. Off bias. On test. Look at that. Let's see if I can get a shock this time here. Okay. There it is. Anybody want to hazard a guess as to what all that means? I never mentioned this before, I'm sure, on a video, but when I was a kid, I built an oscilloscope out of an old TV. There were no triggering or anything like that. I just let the I used the audio amplifier to amplify vertical signals, and I hooked the speaker wires onto the yoke on the neck of the tube. So whatever came out of the audio amplifier would get onto the yoke coil and throw the pointer up and down. And then I just put it, just like I've done here, in fact, exactly what I've done here. I just put an AC signal on the other part to get it to go across like this. And I could get circles, I get funny Lissajous figures of all sorts on there. Here I am, how many years later, kind of doing the same thing. I've just never grown up. That's what's happened here. So I really don't know what to make of that shape offhand. I'm going to read a little more in the manual and try and see, but the fact is we can get that on there following this procedure. Yeah, I don't know what to do with it. There it is. That's it. That's the 3 things I wanted to try with this. I'm going to go away now and think a lot about this stuff and ponder whether it makes sense to make use of any of these facilities. I certainly like the idea of measuring the element current, measuring the plate current in particular. I like that. Okay, well, thanks for watching, and holy smokes, I'm still alive.